bounce back. So that makes us wonder what's wrong with right whales. One of the reasons is, I'm going to show you a map of their distribution, but they hang out really close to shore. And when they're close to shore, they get hit by boats, they get tangled up in fishing gear. And those are really important parts of their story, and it contributes to mortality. We don't really think any right whales are dying naturally. They don't live long enough to die naturally. Humans are killing almost 100% of them. But my approach, and the reason that this is interesting for marine heat waves, is my approach is like Chuck has described a bit. I'm also interested in how prey limitation impacts the population. How endangered are they? I should always point this out. There's only 356 estimated to be left in the species. Here is a modern map of their distribution. We're going to dive a little bit into how this map was made and how it's changed in the last decade. But broadly speaking, they hang out near the coast of the US and Canada. They feed up in these northern areas, and then the females will migrate in the winter south and give birth off the coast of South Carolina, Georgia, and Florida. Sometimes there are a few tag-alongs, males or juveniles that will come with them on that migration. But it's a must-do for pregnant females. I also should point out that the migration south and the time spent in this calving ground, there's really no prey available. There is a budding area of interest. Could the right whales be feeding here, maybe in the northern part of the Mid-Atlantic Bight, but surely not in the southeast US. The reason that prey, I thought, was a really interesting way to approach changes in right whale demographics has to do with reproduction being really energetically expensive. So we don't really see right whales starving to death. We don't think that's a cause of their mortality. They will starve to death sometimes if they're really tangled up in fishing gear and they can't feed because of their wounds or their entanglement. But they're not really naturally out there starving to death. But right whale reproduction rates change really dramatically. And here are some clues as to why. Carolyn Miller published a paper saying how thick is right whale blubber. And she found that right whale females, right before they become pregnant, have a really thick blubber reserve, much thicker than all of the other demographics. Another way to think of that is you have to get a really thick blubber layer if you're going to successfully get pregnant or sustain that pregnancy and give birth to a calf. Here's another study, this one by Sarah Fortune. Sarah did a nice bioenergetic model and said, how much food does a right whale need given its demographic stage? And it's pretty consistent for all demographic states except for nursing mothers. Nursing mothers, as you'd expect, they're maintaining themselves and they're maintaining another animal. So they need something like double the calories in a given day. So here are some clues that while we don't see prey limiting population survival, there's a possibility it could limit reproduction. I like this one the best because people love pictures and this feels very easy to understand visually. This is a picture of a female right whale right before she gives birth. So she's really fat, right? You can see this kind of bulgy back. She's got a really thick blubber layer. Here is a female right after she's finished nursing her calf for a year. So she's used all that blubber, turned it into milk and fed it to her calf. And you can see now, instead of this nice rounded back, you see this dip behind her skull, right? So that blubber layer is thick, right? So clearly there are big changes happening in the blubber, once again, making it possible for prey to be important for right whale reproduction. So this is an older map, and by older, I mean 7 years ago, of right whale distribution. We used to think of them feeding just up here in the Gulf of Maine and along the shelf of Nova Scotia here. And then, of course, they come down to the southeast like I described before. When they're up here, they feed on Callinis finmarchicus, which have been well introduced. Chuck mentioned this lipid sac, and you can see this outline right here. Oh, cool, I can drag my mouse. This outline here is the lipid sac. And that's really important because, so what Chuck said was the copepod builds that lipid sac so that it has energy when it goes into diapause. It hibernates essentially on the seafloor for a few months and it needs food to survive. So that's why it makes the lipid sac. But from the right whale's perspective, that's the only zooplankton out there that's really worth eating, because that lipid sac makes a single bug so calorically dense. So that's why our right whales target these guys specifically. And in this talk, I'm largely just going to say that reduced prey, right, changes in this bug, Calanus finmarchicus, can cause declines in calving rates. And then we found that it can cause abrupt changes in right whale distribution. And now I'm going to show you data and models to prove those things. Let's see, what else do I want to say about Calanus? I love this paper, written by Ray Gondot, 2010, since 2011, and it maps the distribution of Calanus in the North Atlantic. And so you can see, there's this line that Calanus won't go below, but mostly right whales are going to be interested in what Calanus is densest, so those red and yellow spots. This red spot right here is the Gulf of Maine. So according to this whole basin distribution, right whales are feeding on this bug at the southernmost tip of its range, right? That's really really important, because we know with climate change, a lot of animals are shifting forward. So in this case, if this animal shifts forward, then right whales are going to be in trouble in some way or another. And so Ray Gondot did these projections and said, where will Calanus be in 2050 and where will it be in 2100? And we see even in 2050, that bit of Calanus, that hot spot, it disappears. Right here's the bit of oh, maybe I should stop touching. But you can see that red patch in the Bay of Fundy and the Gulf of Maine has disappeared. Okay, so this alludes, before we've had any right whale crisis, that a problem is coming. So you've already seen this. I use a lot of CPR data. We use some other data later in the talk. But the one thing I want to bring up, since it was already really well reviewed, is we did break it up into these boxes. In this case, we labeled it Massachusetts Bay, West Gulf of Maine, East Gulf of Maine, and Scotian Shelf. And we do use these boxes as some sort of coarse spatial information to try and better understand how right whales are using their prey. This should say C5 and C6. I'm just gonna bring up that terminology. These copepods, they go through a lot of life stages. The last part of their life are their copepodite stages, and they go from 1 to 6, where 6 is an adult that's reproducing, that can reproduce. The reason that you see us keep talking about late stage Calanus, or like C5, copepodite 5, or copepodite 6, is because that's the stage that builds up that lipid sac that's caloric enough to be nutritionally valuable for the right. And that was sort of an important distinction. If you remember in Andy's paper, he talked about the Calanus 1 through 4, and then the Calanus 5 through 6. The reason he broke those up is because it's those late stages, C5 and C6, that are actually contributing to right whale nutrition. So the first question we're going to approach is, do natural climate oscillations influence right whale demography through prey? And we're going to go dive into the history of some of the things that Chuck talked about when he showed off the LNO paper with the AO and the AOO and all of those, how they feed into right whale calving. We're going to dive into how we use that data to feed some more sophisticated models. You've seen a version of that slide. I'm going to go through this fast because Chuck already did, but what I want to point out here is that when that Beaufort gyre spun down, as the AO became more positive, right, that pressure gradient got big, the AOO became more negative, and that released the Beaufort gyre's water. We think about it with a lag because it takes that water a few years to come down and enter into the Gulf of Maine area. But when it does, it definitely has this signal where the late stage, those older Calanus finmarchicus, they decline. Okay, so this was a really compelling relationship. And Chuck already described this one as well. This is more of an event style. I mean, sort of in the way that you think of marine heat waves, right? The AO is good at describing generally the freshness and the saltiness of the water. But here, when there was that dramatic year in 1996 that the NAO did that precipitous drop, we saw a lagged extensive decline in the Calvinist and Marchicus in 1998. So just keep those, Chuck described them really well, but keep them in the back of your mind because they contributed. This is again that Calvinist time series. They contributed to this decline in Calvinist in the 1990s, and then the right whales responded. So that figure that he showed you where the right whale calf births didn't line up great with the Calvinist index. The reason for that is because, as Chuck described, right whale calves is not really a good metric for reproductive efficiency. Because as the population growth changes, there's more or less females available to reproduce. It's actually even more complicated than that. And I'll show it to you once we've got a schematic that'll be helpful. But this right whale calving index is just the number of calves born in a year divided by the number of females that could have possibly reproduced that year. So it's really saying, how well did you do based off of the maximum number of calves you could have possibly given birth to this year as a population? And when you put it together like that, the relationship is really compelling between the food and the reproductive efficiency. And then I like to put this, it's just a simple figure showing the actual right whale population size. There's probably some discovery curve as we were getting to meet new whales here in the early 80s. But the population, the total size, it goes through this period of growth. And then in the 90s, it doesn't decline, but the growth really stagnates. And then in the 2000s, it grows again. I like this figure because I think it's just a really simple and compelling way to say, when the number of births decline, it affects the whole population. You know, they need new calves every year to keep steady growth rates up. This is why I'm going to show you what the right whale reproductive cycle looks like, and it really matters that you take that into account when you're thinking how many right whales reproduce this year. A typical healthy right whale reproduction cycle should last 3 years. An adult female would spend a year building up a thick blubber layer. The gestation or pregnancy lasts about a year, and they seem to lactate or nurse their calf for a year. After they're done nursing, remember that skinny picture of the right whale, it takes another year to build that blubber layer back up so that they're ready to do the cycle again. So in the ideal case, there's tons of food in the water, the animals are healthy, a female could give birth every 3 years. That never happens for us. It happens in the southern right whale. So it is a very realistic model. It just doesn't happen for us. So by drawing the schematic and building a model that follows females between these stages, we're able to better ask the question, how is prey impacting you on this reproductive journey? So essentially, I built a Leslie-style matrix model that is looking for the value of these two transitions. What's the probability that you're going to transition to pregnant? What's the probability that you're going to transition from pregnant to nursing? Because there's a possibility that you get pregnant and then you lose the calf. And a prenatal or a neonatal mortality, the researchers didn't see the calf. So those are the transitions that we're really interested in this model. And the question is, are those probabilities consistent through time, or do they depend on environmental factors or perhaps prey? I'm not going to go through the goriness of putting the model together, but here are the outputs of the model put together in a few different ways. In all of these time series, the black line is the same, and it's just the number of calves born each year from the population. The colored lines are the model output. In this top one, the blue line is a model that just assumes reproduction transition probabilities are constant through time. Okay, that number, this blue line wiggles because the number of females available each year varies. But we're assuming that it's constant through time. And you can see that the model doesn't do a good job capturing, the blue doesn't line up with the black. It doesn't do a good job capturing the true calving rates. This green model takes Calvinus and Marchicus late stage, averaged across the entire Gulf of Maine CPR transect over a year. And we built in lags. I think this one might have a 2-year lag. And you can see that the annually averaged Calvinus across the whole CPR tract does actually a really good job of predicting right whale calves. So this is pretty compelling evidence that calving is driven, at least in part, by prey availability. And then because it's never enough and scientists always want to get fancier, I tried a little bit of spatial and temporal resolution. I wanted to ask, what if we break that count, the CPR track into bi-monthly periods, and across those regions that I showed you, are there certain regions and seasons that are more important for predicting right whale calving rates? And that's this red line. And this one by far, I mean, from your eye, it might not be that obvious, but statistically, this one is by far the best bet. What ended up being really interesting about that third model, where we broke the CPR transect depth into regions and seasons, is that I tried every single combination of region and season in every part of the model. But it turns out the ones that performed the best actually made some sense for what we understand about right whale foraging behavior. And I'm not gonna, I wish there was a clock in here.
125.
I'm not gonna spend too much time on this. But right whales, so this is just an idealized model of 2 years in a female right whale's life, starting with January, going to January, going to the end of the year. Okay, and here in a case where she's giving birth, this is when she would get pregnant, 1 year in, and then this is when she would give birth to a calf, and then researchers could follow her, would see her lactating with her calf. So it's just an idealized timeline, and then these are the periods of prey that ended up being important for predicting that calf. Yeah, predicting that calf would be born. And so it turns out that in the late winter, early spring, across the entire transect, that's an important prey index for predicting whether or not a female is going to get pregnant. The other important one was this one in just the West Gulf of Maine in the winter. Now, the Gulf of Maine in the late winter and spring, it made a lot of sense to us. We know they're feeding in Cape Cod Bay. That's the time when we think they're sort of feeding the most actively. It also makes sense sort of for the life cycle of Callinis. As Andy said, they're spring bloom specialists. So the Callinis are doing really well just at that end of the winter, start of spring. This one was a little bit more confusing. And then we realized that another biologist, Tim Cole, had just published a paper saying that he thinks this area at this time of year, November, could be an important place for right whales to come together and breed, right? They actually mate in these crazy surface active groups. And if the prey is good, it seems like there's a reason for them to come together. Everybody's well fed, they're not out foraging, and there's some amount of prey available in the area. So that could actually be a signal that prey is giving them the opportunity sort of behaviorally to mate. Okay, so those are the two important prey indices for getting pregnant. And then finally, the East Gulf of Maine in the summer seems to be really important for whether or not that pregnancy carries to term and the female can give birth to the calf. And if you put them together, this is that transition probability over the full 30 years of the time series. And what we're seeing, this red, just like on the last figure, the red is the probability of a female getting pregnant. And that's where most of the variability is. From year to year, depending on the prey, a female could have a 20% chance or a 40% chance of getting pregnant if she's in that right part of her reproduction cycle. And that might not look like a lot, but it is a lot, right? It's like double the chance. So that means prey is pretty important. And then the kind of flashy but unusual signal that comes in here is that transition from pregnant to nursing. And what this essentially is saying is once a female is pregnant, she's probably going to give birth to a calf that's at least going to be sighted by a researcher. They'll take a picture and say, ah, yes, she was a mother this year. But there were 2 times, one being very dramatic, when the prey was so bad in the East Gulf of Maine that even pregnant females were predicted to lose the calf through a neonatal or prenatal mortality. And that is the time that triggers with that large drop in the NAM. So this is pretty interesting and insightful way to think about how does demography, how is it associated with environmental variables, with calories that we've already seen it so deeply relies on circulation, temperature, and salinity. Oh, and here's one more figure I made. If you're a right whale biologist, you like to think about the interval between births. I told you that 3-year birth interval is ideal. And that's why I put a little red line here at 3 years. It'd be great if our females were giving birth every 3 years. But in the North Atlantic right whale population, they're not. And this is a model-derived estimate for what that interbirth interval would look in a given year if that prey scenario was happening for a long period of time. It's like a snapshot description of the foraging environment. And so what this is saying is in the 1980s, right whales would have an interbirth interval of about 5 years. In the 90s, not counting the worst 2 years of the 90s, the interbirth interval was something like 6 years. So it would take a whole additional year to build that blubber layer to be thick enough that you're going to successfully reproduce. But I didn't factor in these 2 years, 98 and 99, because the prey was so poor that if I factored them in, the interbirth interval for that decade would have been longer than the lifetime of the whale. Essentially, like reproduction really slammed to a halt during that period. And then back into the 2000s, the Calanus returned, and that interbirth interval looked like 5 years ago. So everything that you've seen using that 3-part model was looking at Calanus, sometimes annually averaged Calanus, sometimes those seasonal and regional indices. But I also tried in that same model to say, what if the transition probability between reproductive states depended on some environmental variable, like the NAO or the regional slope water temperature, which those are the 2 variables that we use to say that Labrador subarctic slope water is dipping down and potentially blocking infection of those bugs into the Gulf of Maine, right? That's what happened in 1996 and then caused the decline of reproduction in 98 and 99. And so we see that in here, the green boxes say that the variable is doing a poor job of predicting right whale calving. And the orange and red boxes say that variable is doing a good job. And down here, we've got a lag. So NAO and regional slope water temperature with a lag in the range of 3 and 4 years do a pretty reasonable job on their own. Like we're not even looking at bugs. We're just looking at these 2 environmental variables. And probably a lot of this is because of that huge crash that happened in 1996. It sends such a strong signal that it captures a lot of the variability in the data set. And down here we have the story that Chuck was telling with the Arctic oscillation, the Arctic oceanic oscillation, the regional shelf water salinity, and the phytoplankton color index derived from the CPR. And so here that's pretty interesting because we see this pattern in the lags, where the more distant the phenomenon is from right whales, the longer a lag is required for that variable to do a good job of predicting right whale calving. So the AO lag is something like 3 years. The AOO lag is in the 2 or 3 year range. The shelf water salinity index is in the 1 and 2 year range. And the phytoplankton index, that color index from the silk gauze and the CPR, is at the 0 and 1 year range. So it's really cool to have seen that cascade in lags as these environmental variables go from sort of distant to close to the animal. So that was great. I think it's really important because we're able to say quite clearly, and I think convincingly with the data, that the prey does a good job of predicting calving. Okay, you can't say that for all animals. A lot of baleen whales aren't having this prey limitation, so you're not going to find that same relationship. So that was really great, but right whale biologists and managers really just want to know how the population is doing. And so we took that and we put it into a much fancier model. This is a mark recapture model. The way a mark recapture model is instead of following a group of animals, like your lactating females, You follow every individual animal as it transitions between life stages. And we can do that because we can identify right whales, as Abby mentioned, by the callosities, these white marks on their head. So we know pretty much every animal in the species. Built this model to have whales transition between these demographic stages. So here's the newborn stage, and then the females go up in the schematic and the males go down. If you're interested in demography and population size, you're mostly just interested in the females because that's what's limiting calf births. So the females go into this juvenile stage and they'll stay there for about 8 years, and then go into this adult stage where they can transition, just like in the last model, between these 3 different reproduction stages. So they've been named a bit differently, but it's the same idea. You know, pregnant, nursing, and building that blubber layer. They're represented in each of those stages. And then males down here, juvenile and adult, and then dead in the middle. So what I did is I took annually averaged counts across the whole CPR transact, and I tested it in every single transition in this model. And thankfully, I got what I thought I was going to get. But, you know, does callus impact mortality rates? Right? Observationally, we don't think so, but we tested it and it doesn't. So all of these numbers in this whole model are black, except for this one. The transition from adult to calving, did you successfully reproduce, is colored because that's the one that callus was important to. You can see in the black numbers, like the chance of a newborn dying is 5%. The chance of an adult female dying is 3%. The chance of an adult male dying is only 1%. This is also not a great thing if you're interested in the population growth. You want those females to stay healthy and have long lives. But this, of course, is the part that I was interested in. On average, these animals have a 25% chance. If a female is available to reproduce this year, she has a 25% chance of successfully reproducing. That means she'd reproduce every 4 years, plus there's 2 more years in the reproduction cycle. That's an average of 6 years, and that checks out with what we saw earlier. But in fact, this number varies, and that's what this figure shows. What is the change in the calving probability, this blue number, as C. finmarchicus, as the copepod abundance goes from little to big? And it looks like in this case, the chance of giving birth can vary from 10 all the way up to 35%. That's really dramatic impact on reproduction rates. And then down here, this shows now that you factor in prey-driven reproduction, what does that have to do with the total population growth? And when prey is really poor, the population isn't going to grow at all. And when callus is abundant, then you could have, you know, something like 5% population growth. Which 5%, right whale biologists would be pretty happy with that. Another fun thing about this model is we can use it to project forward. We can make up conditions and say, what's the population going to do in those conditions? And so I did that, but instead of making up numbers, and people would say, where did you get those numbers? I took callus that we'd seen in the 1980s, that we'd seen in the 90s, and that we'd seen in the 2000s. And said, well, if the 1990s, that low callus decade, persists indefinitely, what does that mean for the population? And that's what these green simulations represent. In 100 years, under those 4 prey conditions, the population is still going to grow. All right, prey isn't so bad, calving rates aren't so poor that it spells out extinction for the whale. And that was actually a really important result. Okay, prey is important for population growth, but right now, as we see it, it's not driving them down. Of course, in the 80s and the 2000s, the population growth is much better. I'm going to go a little bit longer. So we answered the question, does prey impact right whale reproduction? And yes, it does. Now, does anthropogenic climate change impact right whale distribution and demography through prey? You've seen these figures before, and the thing I wanted to show you was, hey, it looks like in a couple of decades that callus is going to leave the Gulf of Maine entirely. What's that going to mean for right whale? In summer of 2017, we found out like a hammer to the head. There was a huge event, and the right whales all of a sudden weren't doing well. So this figure was produced, I think, by NOAA, and it just shows the number of right whales that were seen dead in each country in each year. Right whales are dying all the time. Humans are only observing a fraction of those, maybe something like 25%. But in a typical year, we would see about 3 right whale deaths, right? In this case, blue is US, red is Canada. So we saw 3 US bodies, 3 right whale bodies in the US in 2012 and 1 in Canada. But it always stayed low until the year 2017. We found 17 right whale carcasses. The most interesting thing about these carcasses is where they were found. So this is the Gulf of Maine and the Scotian Shelf. These polygons, yellow and green, are the protected areas. Those are the critical habitats where we think of how can we protect whales from getting killed by humans. And we saw a few deaths here around Cape Cod Bay and 1 way offshore near their protected area. But 12 of the carcasses were found in the Gulf of St. Lawrence, where there was no protection because we didn't expect right whales to be there at all. So a big thing happened. And I think I set this up in a way that you can already guess what happened, right? If the prey shifts forward and the whales follow because they have to eat, they're going to venture into unprotected waters. But it's one thing to know it, and it's another thing to show it. When I published that paper that I showed you before with that complicated mark recapture model and the forward projections, I was publishing it literally as this mortality event was going on, which put us, I think, in kind of an awkward position. But I threw in a projection to say, what if more whales die every year? How does that affect the projections? And it turns out if there are 13 more deaths, which is essentially what we saw in 2017, if there are 13 more deaths every year, that's enough to send the population to extinction, right? They can't handle that level of mortality and survive. I did this to not be too pessimistic. I did this using the full Calanus data set, the full 30 years of Calanus, which is mostly good prey years, all right? But when I repeated that projection in private with just the bad prey years, it's a lot uglier, okay? Because you need calf births to sustain the population when the mortality rate goes down. Hint that this was some sort of environmental prey-driven catastrophe shows up when you look at the calf births. This is a time series of the calf births counted for 10 years. The year 2009 is the best calving year that we've had since we've been watching them since 1980 with 39 calf births. But we were still expecting births in the 20s. And then in 2017, there were 5 births. In the winter of 2018, right after we counted those 17 bodies, 0 calves were born. That had never happened before. Chuck mentioned 0 calves born in 1998. It was actually 2. This was a huge shock to not see any. And then even years 2019 and 2020, the calf births were low. I don't think Andy presented this figure. I love this figure though. Andy wrote this paper showing that from sea surface temperature, what you guys are interested in from marine heat waves, the Gulf of Maine is warming faster than 99% of the ocean, which is crazy. But we're also thinking, what about down below? This is my favorite part. I am going to give you a version of that. This is my favorite part. I think that the ocean conveyor belt and meridional overturning circulation is just the coolest thing. And it's complicated and I don't understand everything, but the more I learn about it, the cooler that I think it is. You guys know the global conveyor belts and the AMOC, Atlantic Meridional Overturning Circulation, is just the Atlantic's portion of that conveyor belt. And it's really important because that's where deep water formation occurs. The Atlantic is saltier than the Pacific. And when the water is near the poles, it gets cold, right? And cold and salty water is dense, and dense water sinks, right? So it's pretty simple. The reason the Atlantic up here is so salty actually has to do with the AMOC. So this surface part is in red, right? The subsurface part is in blue. The surface part of the AMOC takes that salty equatorial water and it brings it forward. So the reason water near the equator is salty is because there's more evaporation than precipitation. So it's just saltier water. And unlike the Pacific, that salty water gets dragged north. So it's bringing that salt up, and thus it's seeding that deep water formation, which pushes the whole ocean conveyor belt along. Right, so the process of the AMOC is the reason the whole global conveyor belt works. This cold blob is really interesting. Models and observations both show that if the AMOC slows down, and the AMOC, the surface component, is this Gulf Stream that then shoots across to Europe, makes Europe a nice, warm, toasty place. If this slows down, then less warm water is going to get shuttled across the North Atlantic, and you're going to get this cooling. Right, it's not just because of that decrease in the volume of warm water that's being transported. There's atmospheric effects too, but that's a part of why this cold blob forms. And scientists are becoming increasingly sure that the cold blob is a mark of the AMOC slowing down. In fact, that's what this figure is. I love this paper. It was just published a couple months ago. When Abby was getting ready for her Q exam, she comes to my office. And she's like, we got to talk about the kids. And I was like, I read this paper. It's so good. I love this paper. So Ramsdorff published it in Oceanography. And here he's showing the temperature anomaly of this cold blob as we've measured it over time and using proxies for before we're measuring it. And we see that the cold blob is getting colder. And that's how it's one of the key ways that we measure the strength of the AMOC. As that cold blob gets colder, that indicates that the AMOC is slowing down. There's something else I wanted to say. And then Chuck described, and I'll show in a second, that another signal of the AMOC slowing down is that Gulf Stream. It changes position. It goes farther, closer to the coast, and it gets pushed upward. Closer to the coast, by the way, is a problem if you care about sea level rise and you live in the southeast US. Because the Gulf Stream is literally going to be pushing more water out. I guess I didn't talk about this. The reason, yeah, I think AMOC is simple. The reason the AMOC is slowing down because of climate change is as the globe is warming, the water is warming. Warm water is less dense than cold water, right? So now we've got warm water. If the warming in the pole is creating ice melts, now we've got fresh water. Fresh water is less dense than salty water. So we're getting this input of warm, fresh water where we're used to having the cold, salty water. So it's going to stop that deep water formation. Then a little tricky thing about the AMOC is if that deep water doesn't sink and push that conveyor belt forward, that's going to slow this surface portion. It's going to slow the whole conveyor belt down, right? But as that Gulf Stream slows down, remember it's the Gulf Stream that's bringing the salty surface water from the equator towards the pole. So it's one of those feedback loops. As the AMOC slows down, there's going to be less salt transport forward, and that's going to further slow down the AMOC. It's one of the reasons scientists are so concerned about this, because it's a negative feedback loop. And Chuck talked about, and we'll talk about really quickly, and then I'll free you, how we're seeing the warm water in the basins of the Gulf of Maine and along the shelf. I'll show that to you in a second. But I wanted to point this out. Vince Saba wrote a projection saying, you know, how is oceanography going to change in Northwest Atlantic under these different climate regimes, incorporating things like the AMOC slowing down and changes in the position of the Gulf Stream. And a big takeaway of his paper is that these big global resolution climate models don't have fine enough scale bathymetry to resolve what's happening in the Gulf of Maine. And so when he uses fine scale bathymetry and fine scale spatial scale in his model, he finds that this warm water can be entrained in the Northeast channel into the Gulf of Maine. This is a signal that this higher the lower resolution, coarser resolution climate models don't see it. So this was a really important result, and it really helped us think through our story. Because now we have models showing that there is a mechanism for this warm water to come into the Gulf of Maine. And then real quick, going through what Chuck said, as the AMOC slows down, and as Vince Sava showed with his models, there is this path for warm water to enter into the Gulf of Maine. And the Gulf Stream is shifting north as the AMOC slows down. So that's giving us the warm water. And the Northeast Channel is giving us the passage. And so what we saw in the year 2010 is that happened. The Gulf Stream shifted north. And that's what these red bars say, is that north wall shifted farther north. Chuck showed this figure. This is deep water temperatures at like 150 or 200 meters measured in situ. So when that Gulf Stream shifted north in 2010, the deep water temperature shot up. The Calanus fin. The Calanus finmarchicus didn't like it. So in 2010, they shot down. And I used my old model from years and years ago to say, what was the threshold of Calanus that the whales really didn't like? And then they would lose their pregnancies. And I plotted it here. It was something in the negative 0.75 anomaly. And the Calanus shot down so low that, according to the model, there would be prenatal or neonatal mortalities, according to this old model. And then finally, we saw in the 2010s, this big decline in calf births. And I'm gonna put it all together, which Chuck already did for you. And I think this is the last figure. This is another, just really simple, what's going on with the right whale population. They were doing well in the 90s. They were doing great. They were doing okay in the 90s. Remember, the births were slow, but then compare that to the 2000s when births went up, the right whales were doing great. Then they stagnated and shot down, okay? And part of that shoot down is that reduction in calving that we showed you on the last slide. But there's also that 2017 mortality event when all those bodies are found in the Gulf of St. Lawrence, and that mortality event has sustained. 2018 wasn't so bad, but 2019 there's another, I think, 12 deaths that year. And right now, NOAA has declared the UME, the unusual mortality event for red whales, is ongoing. And that leads us to a 10-minute break. And when we get back, we're going to ask, how has climate influenced the spatial and seasonal shifts in red whale distribution?